welcome to another computer vision tutorial. I come with very interesting news. We will be starting a new code along series on object detection, classification and segmentation using different frameworks, several frameworks. We are just about to start it. As I said, it will be a code along, so everything will be taught from scratch and will be done step by step. So today is going to be the first of the series of tutorial. So today's tutorial will walk through how to design, train and evaluate convolutional neural networks, what is generally known as CNN, from scratch, and then we'll use it to solve a big societal medical issue. That's we are going to select skin disease classification today. So we will ultimately classify skin disease images. We have skin disease images which will build a neural network CNN and use to classify these diseases. So let's begin with the foundation. What are neural networks? Now, neural network is a computational model inspired by how the human brain works. It generally consists of a layer of interconnected nodes or neurons. Each of these are capable of learning small piece of overall patterns in data. At its core, a neural network receives inputs, processes them through several hidden layers using weighted connections, and then produces an output that should approximate a target value or a target class. Neural networks are powerful because they learn patterns automatically from data without needing explicit feature engineering. So, as we move from simple tabular data, which is conventional in traditional neural networks, to images and videos, right? The focus of this channel. Traditional neural networks struggle due to a large number of parameters and the spatial complexity of visual data. Of course, for visual data, everything is converted to zeros and ones. Every tiny details is converted to digits. Now, this is where convolutional neural network comes in. CNN itself is a special type of neural network designed specifically for image and spatial data analysis. So what is the core idea behind CNN? Instead of fully connecting input pixels to every neuron, which is generally how neural network works and can be computationally very heavy, CNN uses what we call convolutional layers that applies filters and kernels across local regions of an image. Each filter extracts specific features such as edges, corners, textures, and shapes. These features are combined layer by layer, enabling the network to understand hierarchical representations from low-key edges to high-level subjects. So what does the structure of a CNN look like? All right. So here you see that a convolutional network composed of several layers, right? We have the convolutional layer, the first, which is to learn spatial features via filter operations. I've already explained that. Then we also have another layer called the activation layer, the ReLU. Now, here, this introduces non-linearity to the network so that it can model complex patterns because, of course, most patterns in real life are really linear. We also have the pooling layer. Now, what does the pooling layer do? It reduces spatial dimension and computation by summarizing feature maps. We are going to explain this in more details when we are writing our code for this, when we are actually designing this. We also have the fully connected layers, which integrates learned features and finally makes the final prediction. You can remember we are looking at classification. So let's say in an image you want to know if what you have is a car, a truck, and a bus. So it's going to make final prediction. The probability of that image being a car, the probability of that image being a bus, the probability of that image being a truck. All right, so it then gives the probabilities. So why as CNN superior for image. Remember I said um CNN was actually designed because of the shortfalls of traditional neural networks with spatial data like images. All right. So first of all, why are images CNN this superior? One is parameter sharing. The same filter is applied the entire image, drastically reducing the number of parameters. We are using only one parameter across the entire image. Also, we also have what we call translation invariance. CNN can detect features regardless of where they appear in the image. We also have efficient learning. Learning is always efficient. They can learn visual hierarchies from simple to complex patterns. Now that we understand neural networks and what CNN do, we need a framework to implement this efficiently. We need a framework, just like all Python tasks. It's not just knowing the method to use, but we also need the framework to implement it efficiently. That is where our TensorFlow comes in. So what is TensorFlow? TensorFlow is an open source machine learning framework developed by Google. It provides a comprehensive ecosystem for building, training, and deploying neural networks, from research prototypes to large-scale production systems. What are the key features of TensorFlow and why is it loved? First, we have ease of model building. With Keras, which is one of the high-level APIs of TensorFlow, you can design models quickly using either the sequential or the functional API. We'll use the sequential API in this our tutorial. We also have the feature of automatic differentiation. TensorFlow computes gradients automatically for back propagation. It supports both GPU and TPU, allowing for large-scale training using accelerated hardware. Also, and very importantly, deployment flexibility. Models can be deployed on the web, on mobiles, or cloud platforms. Uh, Models built with TensorFlow, right, can be deployed on web, mobiles, or cloud platform easily. Finally, scalability. TensorFlow supports distributed computing for big data workloads. Great. Now, for this tutorial, we will use the International Skin Images collaborate ISIC dataset. You can find that it's one of the open source datasets. It contains thousands and thousands of labeled demoscopic images. The project we built in Python, as I said, using TensorFlow. So unlike other tutorials where we use the Visual Studio Code, for this tutorial we are going to use the Colab for design, to make our design. Why? Because Colab has almost all the libraries installed, so we will not need to start installing from dependencies from scratch. And also Colab has some GPU, right? Some free GPU which you can exploit, because computer vision and can sometimes be quite resource demanding. All right, let's get cracking. All right, so this is our Colab. Let's start. So first we will import the necessary libraries. If you can remember, we are using PyTorch. We are using TensorFlow. There's another version of this tutorial that uses PyTorch. So if you want to see how this same this same project can be done using the PyTorch framework, just watch the video on your right, the top right of your screen. First, let's import our library. So here you just this is just basically importing the energy libraries. Of course, NumPy is used for numerical um, analysis. Pandas is used for data frames. TensorFlow is what we are going to use for our computer vision task. So each of these libraries will explain them further. The processing, the model, the layers, the optimizers, and the callbacks will be explained as we are using them. Then of course the matplotlib is used to carry out plotting, because we want to see how the model performs at the end of the day. So matplotlib is used for plotting. So the next thing after that is we mount our we mount we mount our drive, right? We mount our drive. So how do we do that? You can just run this. So let me just run this first, because it's a code along, and then we run this. We mount our drive. Then we direct. This is the directory to the folder where the data is. So I'm just going to show you the data, how it looks like. So you can, this data is obtained from, I got it from, it's an open source data. You can get it from RoboFlow. You can also get it from Cargo. It's free. It's a very large data set. Contains several um skin disease category, several of them. All right, and thousands of data sets inside each of these. But I so many of them, so many of them. But to make it easier, I only focused on the three of the labels. So I got a reduced version of the data set here. It's just basically the same data sets, just all right. So we have the train and the testing, the nevus, the melanoma, and the nematofibroma. All right. So each of these contains several images, which we use to train our model. So this is just one of the images. Okay, so this is it, and so on and so forth. You can just check that out. You can just check that out. So I'll give you a link to this image, to this particular folder. Yeah, you'll be able to access it on my Google Drive. So yes, so that's for the data. And if you notice, the data is arranged structurally. All the train images are in one folder, all the test images are in another folder. All right, that's great. So let's go back to um our collab. So now this is the directory, right? This is where the train and the test folders are, and this, you just add the train here and add the test here. That's pointing you to the test directory and the train directory. The train directory, of course, you can see the path or join joins this and this, right? So it's just basically the same directory. It's as good as saying train here. All right, so here we'll just list the folders are in the train, right, and the folders are in the test, to be sure that they are consistent and that we are also in the right folder. So we see the different diseases as labels. All right, we know that those folders are labels. So I want to create a here. I'll create a dictionary. So let me just take this in. All right, so we have nevus, dermatofibroma, and melanoma. This is just the same thing. All right, so we have here, I want to create a dictionary, because of course you know that when we give our model looks at numerical, does operations on numerical input. So we just change this to numerical input. So it's just a dictionary, so that 0 will mean this, 1 will mean this, and 2 will mean this. So let me just run this, and then we will now see what label dictionary will give us. All right, 0 is for nevus, the multifibra is 1, and 2 is melanoma. Great. So that being done, we'll now move to our next stage, which is um, the data processing and augmentation stage. All right, now this is where it gets more technical. Now, deep learning requires all input images to have the same size and shapes, to have normalized pixel values between zeros and ones. If you remember, when we were looking at OpenCV, when we are describing colors, we look at 0 to 255 RGB, 0 to 255. But deep learning models requires it to be normalized between 0 and 1. So 255 can be 1 and 0 is 0. So every other thing in between should be normalized between 0 and 1. And also, it also requires balanced classes. That means it is no class is supposed to dominate another class. TensorFlow has an image data generator library, which you can find here, which from an image data generator functionality that can help us with some of these tasks. We won't want to do them manually, right? So we won't write them from scratch. So now the question is, why do you carry out augmentation? We've explained why it's necessary to carry out processing, right? Because of course it must be the same size, must be normalized, must be balanced. But why augmentation? First, it helps the model to generalize, right? We augment the data by randomly rotating, zooming, flipping, and shifting images. This prevents overfitting and teaches the model to recognize patterns in different orientations or lighting conditions. Now, what are the different augmentations we could do, or what are augmentations we did for this project, or we are going to do for this project? Um, we rescaled. Of course, you know why this is done. This is just basically for normalization. That's why it's divided by 255. Then we rotate, right? Randomly rotating images up to 5 degrees could be more, right? It defines how much transformation do you apply. Some of these other ones define how much transformation. The rotation, the width shift, the zoom range, those determines how much transformation is you need to carry out. So now the rotation range, this rotates up to this to make the model rotation invariant. Rotation allows your model to see your data from different angles. Let's assume you have a skin, maybe the person shows the skin like this to the computer, right? What if the next time the person is showing like this? The model should know that it means the same thing. It's just basically the same thing. The person just twisted his or her hand. All right. We also have the width shift range, which tells you how to shift the images horizontally. You can also shift the image like this, and you can also shift the image like this, both the width and the height. So here we set it at 0.2. These are not really hard on stone indices. You can decide not to do them. You can just decide not to do them. They are not very compulsory. We also have the share range, which applies sharing, that is slanting, right, to simulate perspective changes, right? Like we may have the skin may be like this, next time it's like this. We also have zoom range. It may be closer or may be too far away. So those transformations, apart from augmenting the data, increasing the number of data that you're using, it also gives the model different varieties. We also have the horizontal slip and of course the validation split. What does the validation split do? That's not augmentation. It only tells you that you're going to reserve 20% of the data sets for validation. Remember, we have when we are working with data sets in machine learning as a whole, we have the training data set, we have the validation data set, and we also have the testing data set. The training data set is what we use to train our data. Validation data set is what we use to select our hyperparameters, while the testing data set is what we use to check if our model can also perform well, right? Can also perform well on unseen data. That means you can your model generalizes. All right. Then of course, when it comes to our test data sets, remember all augmentation are mostly done on all augmentation are done on the training data set. For the testing data set, we will not do any augmentation because we don't want to touch the testing data set. So the testing data set will only do is rescaling to keep it between 0 and 1 for our model. That's all. All right, beautiful. Now that has been done, we know that our data set can be very, very large. Of course, one image is large enough when we change it to pixels, zeros and ones, 0011, 0011, and all that, a large image. We can have several images, like the skin dataset contains thousands of images, right? We will not want to just fit the dataset into we may not have enough resources to handle all the dataset as a go. So, because of that, we carry out what we call batching. We give the data to our model in batches, maybe the first 32 or the first 80 process, then we give the next 32 process this. So that is what this cell does. All right. So we also have a flow dot directory direct a flow dot we have the flow from directory which automatically labels images based on folder names. Which helps us in our bashing to say. So we have the target size here, right? 100 to by 75. That is the target size of the image. So this can help you do rescaling, resizing the image to 100 by 75 pixels because some can be larger than some. So this helps in uniformity. This is the bar size. How many images are feeding at once? So for us, we set it at 32, right? If you can set it at 8, you can set it at 4, you can set it at 64, depends on your computational or 128, depends on your computation the computational resource you have. All right, then we also have what the class, of course, we need it to be categorically, and we subset based on training and validation. Then we will not shuffle. We won't shuffle. So this is just basically the same thing for the training, for the validation, and then for the testing. Right. So now we move to model architecture, which is another very technical part, and this will be the longest part of this tutorial. So please, gear up. Now we build our common, our conventional CNN. As I had explained earlier, the CNN is basically a deep learning model specifically designed for image recognition, right? By looking at the edges, the textures, and complex structures within the images, learning those features within the images. So first, we will tell our network how we are stacking the layers. How are we going to stack the different layers? Uh, Let me just take this. Right. So there are several ways of stacking layers in CNN. What do I mean by layers? Remember, I said that neural network as a whole it's it's basically just like our neurons, right? Each neuron has a specific purpose, and then when they are connected together, they get to form a network which now do incredible things. So now, how are you going to stack those different layers, right? Um, there are several again, like there are several ways of stacking layers in CNN. However, the sequential API in Keras is one of the simplest way to build a neural network. Um, it's called why is it called a sequential? Why is it called sequential? That's because the model layers are arranged in a linear stack. Mm. Each layer feeds directly into the next one without branching or any other shared connections, as you've seen here. Here, data flows from the left to the right one path, no shortcut, no merging. It may be worthy to know that there are other alternatives to sequential. Some of them include functional API and model subclassing. These are largely more complex and can sometimes be grainy, depending on your computational resources. However, most image classification problem can be effectively modeled as a sequence of convolutional and dense layers, right? So for beginners, it is using the sequential is very intuitive and just easy to debug. So now let's go to the first convolutional layer. So we have here what we call block one, right? So this is the building block of the CNN. Is the building block of your CNN. This layer learns basic features like uh, edges, corners, and texture in the skin image. So let's take for example, if the input image shows a male, right, or a mole, probably a mole in the skin, the first convolutional layer may learn filters that respond strongly to dark circular region. Then if it shows something else, it may learn something alternative to that. So it's just basic features since it's basically the first layer. Now let's look at what each of these means. You can see the conv 2D, right? That's just trying to tell that that's just trying to tell that it's a layer, is a convolutional 2D layer, right? Then we have the 3D filter, right, which you can see as 3 there, right? Then the 3 means the size of each filter. So it scans, what it means that it scans 3 by 3 pixels region at a time. Then you now see input shape 175 3. What that means is that if the input shape size is, the height is 75, the width is 100, and there are 3 channels. We have the RGB, right? So you take note of that. That is why you have the 175 is basically the shape, and the 3 is basically the color, the number of channels representing the number of colors there. Then the next one you see here is batch normalization, right? You can see it here. Let's see if I can. All right, so we have the next one we have is batch normalization. What does batch normalization do? Batch normalization normalizes the activations of the previous layer. What do I mean by this? It keeps the output values in a stable region between zero mean and a unit variance, as mean of zero and a variance of 1. It also helps the model to train faster and to reduce overfitting. So look at it like this. During training, internal values can shift. Batch normalization now will stabilize this, allowing for deeper network to converge faster. And then we have max pooling, which is this. So what does max pooling do? Max pooling reduces the special size of the feature maps. It takes the maximum value for every 2 by 2 region, gets a 2 by 2 region, then takes the maximum value from it. That's why you're seeing 2 here. And then you also reduce parameters and computational load, because what it does, it takes, the image is quite large, so what it does, it just takes a small 2 by 2 and then look at how it go process it. So let me just give you a basic example so you understand what this does, since it's a pretty long and experiential class. So now if your 75 times 100, 75 by 100 image becomes is through max pooling, it's reduced to 35 by 50 feature map, right? You have technically half the size, keeping only the dominant features like dark patches, texture boundaries, which may be more important for what you are trying to do. Now, why is this important? It makes the model more efficient and focuses on the most important features, right? Which can say the strongest activations, right? It focuses your model on something on smaller rather than looking at the larger feature map. So we now move to the second layer. So what the second layer is very similar to the first layer. The second layer is very similar to the first layer. Basically the same thing as the first layer. It just doubles this time. It doubles the filter from 32 to 64. That's the only thing you really notice from 32 to 64. Why does it do this? It's a deeper layer, so um it allows the model to learn more complex patterns, right? So it continues to use our 3 by 3 filter, as you can see, and it also uses another pooling here to reduce dimensions. All right, so let's just assume that maybe the first layer detected edges, right? This layer can detect cluster of edges, right? The first layer just detects edges in the pictures, right? Which can then be able to isolate the skin. So this layer could detect cluster of edges, which could say, oh, that's a boil, which could now refer more to a skin category, a skin disease category. So now we will now move to the third layer, which is also again very similar to the second layer, right? Filters again in this case have been increased from 64 to 128. By this point, your CNA should be able to recognize complex textures and patterns like skin tone variation, lesion borders, and all that. So of course, each deeper layer, right, we should be able to capture more abstract and semantic distribution. So that's just basically this, just more elaborate learning from the image, deeper learning from the images. So now, after we've done that, this is basically the same thing too. It's increased again to 256 from 128. So it's basically what 3 does too, but just at a deeper level. Finally, we will now have our fully connected layers. What do we do here? Let's take this one by one. Let's look at flatten. What does flatten do? Flatten converts 3D feature maps into 1D vectors. This allows for data to be fed into a fully connected dense layer because it is easier if the data is processed as a 1D vector than if it is processed as a full-fledged um, feature map, a full-fledged 2D or 3D or a 2D array is easier if you have it as a 1D array. So let's look at it like this. If you have a final feature, let's say 9 by 12 by 128, flattering will make it into a 1D vector 13,824 values, right? So now the next one is the dense. Yeah. So the next one is the dense 512. It means we have a fully connected um, layer with 512 neurons. Each neurons connects to all outputs from the other layers. For one layer, it just means that each of these layers is connected by 512 neurons. Then we have the activation function, right? An activation function, what does an activation function do, which you have here? An activation function determines whether a neuron should be activated or not. It introducing non-linearity into a neural network, which of course is crucial for learning complex patterns. What it does is that it takes the weighted sum of the neurons input and passes it through a mathematical formula, a mathematical function, There are different mathematical functions. For this, you are using the ReLU, which has its own specific mathematical function. And what it does is that it will produce an output that will now be passed to the next layer. Without these non-linear transformations, the entire network will just act as a single linear layer, limiting its ability to model um, complex data. So what are we saying now? It just allows us to learn combination of extracted features. Just learn from combination extracted features. This from here, this from here, this from here. Which when we combine together, it will give a deeper description of whatever whatever, or a deeper description of whatever image you saw. Then we'll now have dropouts, right? Dropout of 0.5. What does dropout do? Dropout randomly drops 50% of neurons during training. Strange, right? Why does he do this? So that to prevent overfitting by forcing the model to learn more about robust representations instead of memorizing. You know, it's more like I'll give you some, but I'll take some out. It's not you can't just learn everything that way, right? It's more like poke gaps into it. When you poke gaps into it, you can now infer, oh, something must be missing here, something must be missing here, something must be missing here. You don't have to learn exactly just the picture exactly as it is, because when we are looking at our model with our test data set, we will rarely see data that will be exactly like the training data set. There will be differences. So the dropout includes those loopholes, which will help our model to generalize better. Then of course we have the compile. So let's look at the compile before we run this. So what happens here? Here we have three major things. We have the optimizer, we have the loss, and we have the matrix. Now, an optimizer, let's start with that. An optimizer in a neural network is an algorithm that adjusts the model parameters, that's the weight and the biases, to minimize the loss function, thereby improving the accuracy of its predictions. It does this. How does it do this? It does this iteratively by calculating the gradients of the loss function and then updating the parameters in the opposite direction of the gradients to find the minimum. This in fact why we choose the type of loss that we have here, the categorical entropy. So you can look at you can I can um, look at that. So in terms of matrix, we choose accuracy. Now there are other classification metrics that we could have used. Example is if you've done, you understand classification. We have the recall, we have the precision, we have the F1 score. We could have alternatively used any of this. It's just a more easy way, right? Accuracy is a more easy and straightforward way to a straightforward way to understand indicate to understand performance. It's why do we have to go for something more complex when we can just use something as easy as that? So finally, we summarize our model. So this will basically display the entire architecture for us to see. That's what this does. It will generally display the entire architecture for for us to see. So let's run each of these. Uh, Sorry, this has disconnected. So let's just so we have this, and then we run this, and then we check the summary. So you can see this is the entire summary, right? All right. So there are about 3,500,000 parameters and 3 million, and all of them are trainable. Almost all of them are trainable. There are almost about 1,000 non-trainable parameters. So then we'll now have what we call the callback. This is another it's very important. It's important, especially if you are training a large model. Now, what do we do in this stage? Here we do two things. First of all, plateauing and also checkpointing. What does checkpointing do? Checkpointing understands that you may train a model while you are training a very large model, something may happen. Either you may not be able to train a model as a stretch, or maybe something happens, someone just kicks your device, or something just stops the training. So you may not want to start from the scratch again. You may want to continue from where you stop. That's what checkpointing does. So what it does is that after some time, it saves the model, right, somewhere, saves the model somewhere. Then when you come, it simply picks that model and then continues from there. You can of course use the model at that stage to do your prediction, right? Even if you've not done complete training. Probably you had 20 epochs, right? That means it's going to train 20 times, it's going to go 20 iterations, right? And then maybe after 10 or after 9, it was something stopped it or so. So I mean, after 10 or 9, something stopped it. So your checkpointing will save that. You can decide to use it if you are too if you are in a hurry, right? Or you are um, desperate. That's the word I could find, right? So this is just that. It uses the evaluation accuracy to know that, oh, because what it does is that it saves it only if the one is saving is better than the old model, right? So this just saves the model as you keep training. Then this is also something very important. Another reason why I really use TensorFlow, they reduce LR on plateau. What it does is that it adjusts the learning rates as progress stalls, right? So remember we had learning rate somewhere here, which tells us by how much we want to learn. Yeah, we had it here, right, as an optimizer, as part of the features or the parameters of the optimizer. So what it does is that it adjusts its learning rate. When you notice that the rate of learning, you're no more learning anything. It's like this method of learning is not learning anything, it now adjusts it, right? So it uses the evaluation loss to know if the model is actually performing well or is just running in circles. So patience 3 means after 3 iterations, if it's the same result you are getting, that means it's not laying anything again. That's after 3 epochs. If it's not laying anything, it should adjust the learning rate, right? So this 0.5 means that you should reduce the current learning rate by 5. Maybe it was too high, so it was not laying anything, like given a class 5 arithmetics to a class 4 person. It may be too high. So what it does, reduce it. They need to understand at a lower level. Then you know that you can't keep reducing. At a point you may understand that it has finished learning whatever it needs to learn. So we must keep a minimum learning rate which we placed at this, so that the learning rate does not become too small, or you just keep reducing the learning rate forever. So this verbose means that you can print you should print messages to the console, so that whoever is using it, right? Whoever is looking at the training can know, oh, that at this point the training process plateaued. All right, so that's that for this. That's what everything here does. This is not the. You can see that there's also variables here, which will also tell you that okay, it got a beta model and we've saved the beta model here over the last model that we have saved. Okay, so we now understand what verbose does in callbacks. Okay, so now let's move to the main training, but let's run this first. So this is very similar, very straightforward and similar to the model of fit we use in machine learning. So this is the nothing really happening part of our project of this. So this is just CNN the fit, right? Is you take the training data, take the validation data, tells the epoch. What this epoch means is that I want 20 iterations. So because of time, we'll just keep this at 1 because 20 will be a bit long. Of course, it will not train well. So if you are training yourself, you can make this higher because 1 will not actually do any decent training. Then we'll now put the call back. We should um, give it the checkpoints, which should be written, and also the reduce error. Okay, reduce error. All right, which is the plateau is how the what you should do during plateauing. These are just parameters. Okay, that being done, we now train our model. So this may now take some time. So we already that's trained for 2 epochs, 3 epochs, three three steps. So each epoch will go for 24 steps. Remember, we gave our data in batches, so it will divide whatever you have by the number of batches that you want. The total number of data set by the number of batches that you set. So we just wait for this. So once you get to 20 over 23, the first epoch is finished. That's that. All right, so it's finished training. Yeah. So the next thing we do. So this is it. The next thing we do will be to evaluate how well is our model doing. So of course, how we do that, we have the for all TensorFlow models, we have the evaluate, and then we'll feed it our test data sets. It's going to give us two things: to give us the loss and to give us the accuracy. We can just print this out or we can plot it. So we're going to do the two. So you run this and then yeah, yeah. And then while that is running, let's look at this. So we have our subplots, right? So this is just basically the history. The history when we use the evaluate, we'll have while it's training, it's saving the accuracy, the validation accuracy, the training accuracy as it is training, right? So after each epoch, it will tell you, oh, this is how well I've done, or this is how well I've done. It's not be so large here because we just used only one epoch. Just use one epoch. So it's going to show you how it was training, the history, right? Where you will now see where it plateaued and you will now see where it peaked. All right, so this is just the plot that will do that. So this is just a basically math plot leaf where we have two plots against two plots, right? On the same axis, right? This is the train and the validation. Remember that this is accuracy plots and this is loss plots. All right. So we have 20 just one epoch here. It should be more here. So let me just run it too. I think that runs. So I think the first ones are finished running. You can see here that their test accuracy is 0.35, which is extremely poor. And then we have a test loss of 1.1, which is not so good too. So this is how the plot is. We are just seeing one here, right? Because we only need it for one epoch, but if you do for up to 20 epochs, this will be more elaborate. So please do for more than one epoch. All right, finally, we can save our model because if you don't save our model, how do we reuse it? So we can use the CNN also, the TensorFlow. CNN also has of course it also has the save, right? It also has the save just as it has the evaluate, which can exploit. So you can simply save your model here and it will be saved at this location. You will see it here. This is it. So now that we have our model, what if we want to make a prediction? What if we want to make a prediction? It's very simple, right? So we use the load models, right, from TensorFlow to load our model from wherever it is. Either I transferred it to you or you got it from somewhere. Then we use this to process whatever image we want to process, want to use. So let's assume I give this the address to an image, right? We are going to load it based on the same size we use in training our model. If you remember, it was 75 by 100. Then we'll now convert it to an array because Python processes using zeros and ones. So we are using tensors. We have to change it to an array. Then we have to normalize it. You know, here we can see have between 0 and 255. So here we have to normalize it. And of course, you know how this is done. You have done it earlier. And then we expand the dimension. Remember, when we are doing our model, we're looking at batch size of 32, right? So here we have batch size of 1 because we have only one image. So we have to expand this dimension, and then we do our prediction. Our model predict just the way we do with our sklearn, and then this is going to give you whatever prediction it is. So now, how does the prediction happen? Now, how does it do its prediction? It will not just class pop up. It will not just pop up a particular class. What it will do is that it will give you a continuous probability of it being this particular object. You know, we have, for example, here we have three classes. We have three classes. Let me just go up and see if we can see those classes here. We have three classes. And, yeah, nevus, dermatofibra, and melamonia. All right. Okay, nevus, dermatofibra, and melanoma. So we have three classes. Then what it will do is that it's going to give you three probabilities. One for the first class, the probability that is for that first class, probability that is the second class, probability that is the third class. It must not usually add up to one, just the probability. And probability per each class is independent. So the one with the highest probability is most likely the one is going to give out. That is going to take. So how do we do that? We take all the predictions, you can see it here, and then 0. That's the first one. The arc marks, then the 0. It takes them. It ranks based on sorts it, right? Then it now takes the first one. Then now remember the first one is 0. Whatever it gives there, what it will do now is that it's going to feed this. This will give you a number. 0 is the first one, 1 is the second one, and 2 is the third one. It's going to feed this into the label dictionary. Remember the label dictionary, we had said, okay, 0 is Nexus, 1 is this, and 2 is this. And then it will change that to the particular category we had set. So let me get an image which we can use with this. All right, so we have an image here, 6.jpg. So it contains 06, 6.jpg. So I try to run this. Right, so you can see the prediction just like I told you. This is for the first class, this is for the second class, this is for the third class. So definitely you can see this, it is more likely that it to be this. We then run it. So which is the neighbor. So it predicts our class at neighbor. We can reuse this model with any other skin. You can just snap if download any skin disease online and then test it, and it's going to work. So that is that for our particular project. So the next one, we are going to try this with this same project, but not using the TensorFlow model. Rather, we'll be using the PyTorch um, model. So yeah, thank you. So if you have any questions, please drop it. And in the meantime, I want to see you again.